Hi guys, just want to say thank you for coming, and there's plenty of pizza, so definitely come up and get more pizza throughout. For those of you who guys don't know me, I'm Zoe Levinson, and I'm part of Traffic 21 in the UTC located here in Hines, and we're the ones that organize these faculty presentations of different research and different things going on. So before we get started, I do have a few announcements of transportation-related activities happening on or around the Pittsburgh area. But before I do that, I am going to pass out a sign-in sheet, so if you guys can just sign in just so we can see who's coming and we can keep you guys up to date of transportation-related things, that'd be great. So we'll start with that. Okay, so the first thing I have is the PCRG, is the Pittsburgh Community Reinvestment Group. They're having a summit here May 12th through the 13th, and they're looking for students to help volunteer at the summit. If you volunteer, it's only 3 hours of your time and you get to go to the summit for free, and it's a 2-day summit. They're going to have over 600 community development planners, developers, researchers, and officials at this conference or summit. So if you're interested, here's some more information of how you can help volunteer with them. Also, the ITS America conference, their annual conference is here in Pittsburgh over the summer, June 1st through 3rd, so definitely register. There's going to be lots of great people at this conference. And they're also having a student essay competition. The deadline for that essay competition is the 17th, so there's still about 10 days before it's due. I strongly recommend, if you're a student, to go on and apply. The prize is going to the conference for free, as well as I think there's some monetary values as well, so definitely check that out. The third thing, and we have copies of all this, so afterwards if you guys want these copies, is Beyond Traffic. So this is like the new thing that US DOT is putting out, and they want your input on what you think the vision of traffic is going to be in 2045. So it's just a lot of different experts in the field. They're all putting their ideas down of what the roads are going to look like and how to start making policy for that. So if you're interested, we have the books so you guys can kind of read, and they're easy books. It's like big font and lots of pictures and infographics at the end. So if you want quick facts about traffic to impress your friends, pick up one of these books. And the last event that we have coming up, which you guys will get emails about, is the Transportation Club. We are now an official undergrad club on this campus, which is exciting. So to kickstart that, we're going to have like a mocktail happy hour at the end of April, and this is for all students, undergrad, graduate, and PhD students. We kind of just want to have like a big open forum for people to see who's transportation on campus and who's not. So it's a great way to network. It's a great way to meet the board of both the Hines Transportation Club as well as the Undergrad Transportation Club, get your ideas of what type of speakers or events you want to see within the years to come. So you'll get an email about that, but that will be at the end of April, the last Thursday in April. So now that all those announcements has happened, I'm delighted that Stan and Zach will be here to present about the connected vehicles.
Thank you, Zoe. So Zoe is our first Women in Transportation Fellow with the Traffic 21 Institute, and doing a great job, particularly with this Transportation Club. It's important at CMU's campus because traditionally transportation engineers are associated just with the civil engineering department at most universities, but at CMU, the transportation students and faculty are throughout the university, and both graduate and undergraduate. And what we're trying to do, and Zoe is doing very well, is trying to bring those folks together from across the university, because as the DOT is looking out in the future, this is the new face of transportation. It's going to be very multidisciplinary and very diverse, and we want to make sure that anyone interested in transportation from across the university is engaged. So thanks a lot. So what I'm going to do, again, my name is Stan Caldwell, and I'm Executive Director of the Traffic 21 Institute, and also Deputy Executive Director of the University Transportation Center here at the university, also here at the Hines College, an Adjunct Associate Professor for Transportation and Public Policy. But again, most of my day job is trying to work with the faculty like Zach and others to be able to get technology, transportation technology from the university applied to real world situations. And one of these that we're going to talk about today is the test bed for connected vehicles that we've actually developed here in the Pittsburgh region. So I'm going to give a quick overview of the test bed, and then Zach will get into some of the specific applications and plans for the future. So first, just with connected vehicles, does when I say connected vehicles, does anyone have a reaction or kind of how you would define connected vehicles? Or anyone have any idea? Yes.
Vehicles communicating with each other with infrastructure.
Good. But so do you have an idea of how that would what mode of communications is used for that? Or
Yeah, so DSRC 802.11.
right. Any other ideas for because a lot of us can argue now that we already have connected vehicles. If your phone is in your vehicle and is operating, whether it's through Wi-Fi or Bluetooth, or you're connected to Waze or any other kind of crowdsourcing system, OnStar, satellite systems, Sirius XM. There's a lot of, and then every major automaker has some kind of relationship with with a communications company for applications that are in the vehicle to keep the vehicle connected, and a lot of that is for navigation or infotainment. But what we're going to talk about today is a little bit more directed towards safety and other applications. But just keep in mind, none of this is siloed to one mode of communication or another. That we have information that's going to help safety, but we have also information that's going to help efficiency, environmental impact, and just your the infotainment of the drivers and the passengers in the cars as well. So it's not siloed. So, just a couple terms we use in this. V2V is vehicle-to-vehicle communication. So, one vehicle sending information to another vehicle. Vehicle-to-infrastructure is communicating between the infrastructure and a vehicle. For instance, if a traffic signal is sending out its signal phase and timing, basically saying, I'm going to be red for 4 more seconds. That's information from the infrastructure to the vehicle. Or the vehicle can be sending information to the infrastructure as well. And then the V to X is, we're starting to see that this isn't really just about vehicles and infrastructure anymore. This could be vehicles to pedestrians. This could be vehicles to the cloud. This could be vehicles to bicycles, satellites, whatever it is. There's now that we're kind of moving into the Internet of Things world, it's kind of an unlimited communications path with the vehicles to a lot of other players out there. So these slides here I actually just borrowed from the Tim Johnson from the National Highway Traffic Safety Administration. Just did a good presentation a week or two ago on where the federal government is with this vehicle-to-vehicle communication. The National Highway Traffic Safety Administration is an administration that focuses on safety of the vehicles themselves. And so the federal government, this is one of their top research areas, is what we call this connected vehicle technology. And their focus is on, as you see up on the screen, the 5.9 gigahertz dedicated short-range communication, DSRC. This is a frequency that the FCC designated to US DOT to be able to have a dedicated bandwidth to be able to use as a platform for vehicle-to-vehicle and vehicle-to-infrastructure technology. So what is it? It's basically just Wi-Fi radio adapted for the vehicle environment. How does it work? It sends out what they call the BSM, the basic safety message. And it basically is just giving every 10 seconds that gives the vehicles location, speed, and heading. And so every 10 seconds, it's just sending out this information. But it's only sending out what we call short range, dedicated short range communication, only between about 300 and maybe up to 1,000 meters. And so as the vehicle's driving around, it's just sending out this beacon saying, here I am, and this is where I'm going. And so it's also listening for other vehicles. And so the only time that that message is needed is if there's going to be an impending crash. If I say, okay, I'm going in this direction, but another vehicle is getting that same information and there's going to be an impending crash, then it can deliver a message back to each driver to warn them of the situation. And again, it can give two different warnings. One, and I've ridden in many of these vehicles that have been equipped with this, and they all have different types of systems, auditory or vibrating seats or flashing lights. But oftentimes they'll give kind of yellow stage warning saying, hey, something, be cautious about a situation coming up, and then other situations of just the big red flashing light that's saying danger now, do something or you will crash. This slide here just kind of gives a nice overview of all the different players involved in this. If you look at the first box in the upper left-hand corner is the auto manufacturers. This is an organization referred to as CAMP, which is an alliance of automakers that are really unified in making sure that this is a standard platform. And then you'll see all the state folks, the university folks involved, public agencies, and industry. This is, again, a very long-term project to deploy this technology in the field. And then, so the significant step from a governmental side happened last February, where the US DOT basically said, we are going to move forward with requiring all future vehicles to have these radios in their car. So instead of this just being science fiction, this is where they made that declaration. Now, they haven't determined how they will actually roll that out. By 2016, they'll actually have a rollout schedule. But in anticipation of that, last year, General Motors kind of stepped forward and said, all right, what we're going to do is we're going to start equipping our vehicles in 2017, our high-end vehicles in 2017, with these dedicated short-range communications radios. And so that's just kind of a general indication in the industry is they expect that probably starting in 2017, this is when new vehicles will be equipped with these. And so there's still a lot on the horizon as far as this slide just outlines some of the research initiatives that still remain out there. A lot of research has been done. The University of Michigan ran a test for close to 2 years on 3,000 vehicles equipped with these radios, and a lot of the infrastructure around in Ann Arbor and Southeast Michigan equipped with these to be able to test the viability of this technology. And again, this data was used for NHTSA to be able to make its decision to say, this demonstrates that if vehicles were equipped with this technology, that 80% of crashes could be avoided. And so that's kind of their data moving forward. And so again, this has a lot of momentum. So yes.
You'd rather save it to the end? I can wait.
No, go ahead.
How did they come up with 80%? Is this like a series of experiments, simulations, is it just estimation based on observational data?
It's estimation, and there's actually a lot of different statistics that could be used. I've heard anywhere from 70 to 90%, and sometimes they'll use in paired crashes or others. But for their decision, there were actually two major applications that they based their decision on. Was that unassisted left-hand turns, which were a major problem, and then also just front-end collisions. Okay, having a car or something stop in front of you and you not notice it until it's too late. So using that, they actually, so if you go to their website, they break down the data and the data used from the Michigan pilot to be able to show their justification for moving this forward. Because the way NHTSA works is, they can, through regulatory ability, they can move these things forward. That's how they did with seatbelts, airbags, et cetera, anti-lock brakes. And so what they do is they say, all right, we've seen enough data to show that it's worth us regulating the automakers to put this in because we see the potential for a significant reduction in accidents.
So the remaining 10 to 30%, is that types of accidents that the system isn't good at detecting at all? Or is it just as the technology gets better, it will slowly creep up?
This right now, I mean, what they're looking at right now, this is connected vehicle technology. I'll talk about this in a minute, separate from any autonomous vehicle technology. So you still, all this is doing is giving a warning to the driver. And so it's still giving a warning to the driver, so there's still going to be incidents where, you know, even if you have enough warning, it's still too late.
It's just human error, no matter how good this technology gets.
Exactly. But we'll get it, but that's where you get in automated technology to help the rest. But if you go onto their website, and I saw it in some of these slides, and I didn't want to overwhelm everyone with that, but NHTSA will have it on their slides. So Pennsylvania, sorry. So right now, you know, there are some of this DSRC equipment deployed in the field, and now we are, you know, we've started to deploy some of this here in Pennsylvania, and we've become part of the affiliated testbed program with USDOT in January. The Pittsburgh region, CMU signed a memorandum of agreement with USDOT to have our region be part of this network of places that are actually testing this technology on the ground. And so we have a lot of partners we're working here in Pennsylvania, including PennDOT, the Turnpike City of Pittsburgh, our local transit agency, and a lot of you know, both local and national companies to actually deploy some of this in the field here. We have 24 signals, traffic signals, that will be equipped with this dedicated short-range communications radios here in the Bloomfield area of Pittsburgh in the East End. That should be coming online around May or June. We have 19 intersections already equipped and operational up in Cranberry Township in Butler County, which is about 20 miles north of the city of Pittsburgh. And PennDOT actually on McKnight, this is McKnight Road in the North Hills of Allegheny County, about 10 miles north of the city. They're putting in an updated signal system on McKnight Road, and just on their own decided to put dedicated short-range communications in there in anticipation of this testbed activity growing throughout Pittsburgh. So again, this is starting to become adopted by PennDOT, not just on our own. PennDOT has really become one of the leading states in in kind of looking at both connected and autonomous vehicle technology. Yes.
So when a piece of infrastructure receives signals from cars, is there any aspect of that signal that can lead to identification of the car itself, or are you only giving information about the car it's moving?
Right now, this is all. It's all just staying within the information from the vehicle to the infrastructure or to the vehicle. They're not. You know, it's anonymized data.
Okay, so
but for the
license plate or
no.
The IDs actually, I think, what is it, every 5 minutes the IDs switch.
okay.
So there's no tracking. Within that 5 minutes you can track, but outside 5 minutes you can't track.
So there. Go ahead.
You can track, there's some amount of concern that you can track across that, but it requires a lot of control.
And right now, DOT, you know, we're talking about in the previous slide and some of the future research initiatives, this whole idea of safety certificates and renewing the safety certificates on a big scale, and they did some of this in Michigan, but to look at this on a big, you know, on a very large scale, it's probably going to be a third-party provider doing that, but that hasn't all been determined yet. And so DOT is still in the process of figuring out, you know, how that will all be implemented. But because privacy and both privacy and security will be major considerations of that.
Minority report.
Yes. Well, it's a major concern. So when we talk about the autonomous vehicles, sorry, we're not. There's kind of two parallel tracks here. With the connected vehicle technology does not require any automation in the vehicles. Automated vehicle technology does not require any connection of the vehicles itself. So these are kind of technologies running on two parallel tracks, but they, clearly connected vehicle technology will augment autonomy. And autonomy, as you brought up with your question before, will definitely augment connectivity. And so they're on parallel tracks, and we're looking at how these will be merged together in the future, and DOT as well. But again, right now these are kind of from the research and deployment side being deployed on two parallel tracks because the timing, the timing is different on each of the technologies. But clearly, we're seeing the eventual integration. We showed this with our Cranberry Township demo where we had PennDOT Secretary Barry Shoak, former Secretary Barry Shoak, and Bill Schuster, the chairman of the House Transportation and Infrastructure Committee, who's from Pennsylvania, did an autonomous vehicle ride from Cranberry Township to the airport, but they were using the dedicated short-range communications equipped signals in Cranberry Township to be able to navigate traffic and the signals on the busy Route 19 in Cranberry Township. So kind of following that ride, the secretary at the time of PennDOT, Barry Shoak, said, wow, okay, we believe this is going to happen, but we're planning right now for 2040 in PennDOT. That's our design, just our typical design range of planning. And so if we take into consideration there's going to be connected and autonomous vehicles in 2040, how does that affect our planning, our design, our maintenance, everything about our whole system? And so CMU did a study for a year on that. That was released in July 2014. It's on the PennDOT website, or you can contact us with information on that. But it's really kind of put Pennsylvania in the forefront, and that's why they're, PennDOT and in this region, in this state, is such a good place for this test bed because they're really engaged. City of Pittsburgh has been, Cranberry Township, PennDOT, the Turnpike, really engaged partners in seeing, okay, how can this really affect the future? These were some of the areas we looked at as far as, again, infrastructure investment and design, communication devices, licensing, et cetera. And PennDOT's moving forward already on our recommendations, as we're seeing on McKnight Road. But now that a lot of this is coming forward, we're looking at the policy implications. So we're kind of developing here at CMU a whole connected and autonomous vehicle policy research center that is actually looking at, okay, if this is going to happen, how's this going to affect everything from the design all the way down to the land use and travel patterns, et cetera. So that's a really exciting area that we're, both from the policy and engineering side, that we're having a lot of faculty pursue. So that's just kind of a general overview again of the existing test bed we have here and the partners who are helping us, and Zach's going to get into the applications.
So thanks, Stan. I'm going to go a little bit more into the technical details of some of these things, but not very deep. If you have any questions as I'm speaking, ask away, and I'll see if I can answer some of them. A lot of this research is not research that I'm familiar with in a deep level, so I may be or may not be able to answer some of those questions. The other ones, some of the other areas I do know better, and we have expertise in-house to answer some of these questions. So let me go on for a little bit more here about what I'm doing. These applications that I'm going to describe here are the technical applications that are just sample points across campus, not only CMU campus, but also Silicon Valley campus, that describe various research that's in this area of connected vehicles. And some of them are more tangential than others, but it gives you a sense of the widespread and how important it is, has become on this campus. So just to give you a sense of some of the research projects just being operated on for this, we recently made a proposal to a big program here, and I'll talk a little bit more about that program a little bit later. But just to give you some of the participants on that program, you see this wide sense of faculty here, people from robotics, people from ECE, from CEE. So you have a large interest in this, and it's kind of forming this nexus that's creating a momentum for this research. So before I go into some of the application descriptions, as I said, they're going to be brief. I want to give you just some sense of a little bit of the backdrop of some of the technology behind it. One of the things to understand here is what is the importance of DSRC radios? Why use DSRC radios over Wi-Fi, over cellular? What are the reasons to do that? And there's no definitive answer. One thing that is definitive is that DSRC provides low latency communication. So things that are going to be really close, that you have no time to react for, DSRC is a very good candidate for those kinds of communications. Beyond that, then it becomes some of it is policy, some of it is privacy, some of it is what's available in those locations, and you have to decide about those things. So I'm going to talk mainly about DSRC communication, but I will try to point out as I'm going along with these applications that other modes may be more suitable for some of these applications than just DSRC communication. So one of the things about DSRC too is that it's still being developed. Protocols are being developed. It's far from set in stone, and I'm not even an expert of that, but every story I've heard has been always some kind of little bit of a horror story about this. The other thing is that while you can see one of the most important things is that if you're in the vehicle and you're trying to get these messages from the infrastructure, from other vehicles, and it's for the humans, you'd like to be able to see those messages, tailor those messages, use a platform. And currently right now, there's not the standardized UI platform that comes with the deployment of those radios into your cars. So, it's just like in the cell phones, well, what do I do for my apps? I can do my Android apps, or I can do my iOS apps, and you're like, why do I have to be two different standards? Same thing applies here. Why do I have to make two different interfaces? It'd be nice to work within a standardized interface. So just some terms here, just so I might use throughout these applications. If I say an RSE, think more of a static placed radio that's powered, not moving around. That's roadside equipment. And the OBUs is usually the one that's in the vehicle, and that's the onboard units. V2I communication, as Stan has said, this is typically from vehicle to infrastructure. I'm going to emphasize that this is most of the communication I'll be talking about will be a DSRC radios to give you that short-term communication, but V2I, I don't think in itself as a term limits you to DSRC. Okay. Same thing, and I to V is infrastructure to vehicle, and the same qualifications hold there. Okay. Hello. Okay. So one of the things I want to talk about is SureTrack. One of the things that really makes it attractive about Pittsburgh as a site for this kind of connected vehicle deployment is that we have control over a number of intersections, as Stan pointed out. And having control over those number of intersections empowers us to use information that can be conveyed using connected vehicle technology. And one of the second step that's really important about that is that it's actually in real world sites. It's in the roads with all that uncertainty, with all the things that are going on there. It's not in some isolated test bed that you can run, very standardized and qualified tests. If you can do it there, as Frank said, you can do it anywhere, okay? I mean, it's going to work, all right? So that's a really important matter to keep in trace. So let me give you just a small sense, very small sense of how SureTrack works, because it's going to be leveraged by a number of these applications, and so you're going to have to understand that, all right? So the way that, at a very, very high level, that SureTrack works, and this is work that's done by Steve Smith's ICL group, and I would be remiss if I didn't say fundamental to that research is Greg Barlow here, who's a postdoc in there, is that the basic operation is that you have an intersection, and at that intersection you have cameras that provide, cameras or radar, that's coming in the new deployment, that provides sensor information about vehicle flows. It says vehicles that are flowing in, vehicles that are flowing out. The ones that are flowing out become advanced detection for downstream intersections, if you can understand that, all right? And so it provides a sense of information, provides presence if you're sitting waiting at a queue, and provides counts of those vehicles, all right? So think of that information as this kind of fundamental, necessary information that you have to make decisions about how long to make phases at a light, all right? So the current traffic conditions are extracted from those sensor informations, and at each intersection there is a box, and you've seen these silver boxes, and inside that we've put computers in there that we've hooked up to the controllers that were already there. And our computers now tell the controllers when to switch phases, with the caveat that you can't break safety regulations. So we don't, the way we were able to get to those cabinets so quickly, because everybody might wonder about the liability of that, is that we don't break the safety things that were already vetted in a process for those controllers. So that's how we were able to get in there. We don't ever break that consideration. So we have we send the detection information to our computers and the controllers. The system computes the phase schedule that optimizes the flow intersection. And basically the idea is that you see vehicles coming, if you think of an intersection this way, and you're trying to optimize it so that you can get the most vehicles through those intersections. All right? It sounds, I'm saying it very simply, it's much harder than that, okay? And because you're trying to do this in, unlike other systems, SureTrack will try to be working within a second or two and trying to reevaluate that decision. So it's trying to solve this problem very quickly. One of the ways it solves it is on a shorter horizon, but nevertheless it's trying to solve it very, very quickly. Okay. Huh?
It's a longer horizon than most of the other systems.
I didn't mean that. I meant for a normal scheduling problem, it's a very short horizon. You know, we're not talking hours here. Okay. It'd be useless anyhow because of the dynamics. Anyhow, this is the normal interaction we have in our lab. So it's all right. Anyhow, so moving on, what happens is that we take the scheduler and we send to the controller, makes the schedule, and it tells the lights where to go. The operating actions that we have basically are stay in the same phase, extend that phase, or let it go and go on to the next phase. And that's basically the only operation actions we have, and those are the decisions you have to make. All right? So we have this sort of rolling horizon. We schedule, as I said, every second or two. The cycle is repeated every few seconds, and then we make that decision, and make that decision, make that decision. Stay in the phase, extend the phase, and there are limits to how far you can extend it or how far you can't cut it off short because there are mins and maxes. And those are sort of set, and those are a little bit tailored. Okay, but the phases you have to stay in that phase. For example, if you have a green phase, but that has to be matched and you have pedestrians walking, you can't make it shorter than it takes the time for the pedestrians to walk across. All right, so you have a min. And the max is going to be something, how long you can stay in that phase. And the reason you have that, partly, and it's an important matter, is that detection can fail. And you would end up starving out on the other side if you just stayed in that green the whole time because your detection failed. So this way you're forced to switch over to give some time to the other side if that detection fails. All right. All right. So let me go on. All right. So that's SureTrack. Just give you a really quick here notion of what it looks like. As I told you, you have cameras up top that gives you the detection. You have the controller, as we showed you. The video boards are processing. Well, not always processing. And in some of our installations, they have processing the video feeds for the detection. And then we have a network connection that allows one of the things that requires that each intersection be able to talk to the other intersection, so we have communication across those intersections. And then we have as I said, the computer in there. And the one other piece that's being added as part of this new bomb center deployment is we're adding the DSRC radios. I knew that'd make you laugh. So I just throw that little radio on there. So in fact, that's sort of what they look like. They pretty much kind of look like that, except for the antennas that drop out of it. These radios are going to allow for this kind of communication with the infrastructure from the vehicles and very quick things. So let's see how we can now leverage some of that infrastructure and the VDI using those DSRC radios. All right, so I've divided the applications. I'm about to describe them pretty quickly because we're running out of time. And I'm going to describe these applications, but I've separated them into two rough groups. All right. One group I'm calling multimodal traffic management, and by multimodal I mean bikes, pedestrians, vehicles. Huh? Modal? It's modal. It is modal. Every other place I'm sure it's AL. You're absolutely right. It's not modal. It's modal. Okay. So it's bikes. It's bikes, it's pedestrians, it's vehicles, it's buses, it's trucks, and they all pose different challenges to our traffic flows. One of the things that's being promoted, especially under the new mayor, not so new now, is this idea of complete streets. And this is the idea of you're trying to get everybody involved in it, okay? And you're not just optimizing for a vehicle flow. So you're trying to get everybody, a lot of that has to do with safety. We'll see how those two things, efficiency and safety, come together, all right, or not come together. So, all right, so one of the first applications I'm going to talk about is, again, out of the ICL group. It's with Steve and me and Greg and Isaac. And this is this idea of using vehicles that are out there on the roads to provide additional information about the sensing. You notice that we said we had cameras and we had radars that are providing some sensing, but if we had DSRC radios saying, well, here's a vehicle, it's sort of waiting along those corridors, or here's the speed movements, or here's the locations, and it hasn't moved in a bit. That by using that information, we get a more accuracy, and especially if you fuse it with the additional information. And now, sensor fusing is always a difficult problem, but if you can fuse that information, then you can try to triangulate and get more reinforced ideas about an accurate sensor model. The better the sensor model, the better SureTrack will run, the better any of these adaptive traffic light signalizations programs are going to run. All right. So this is the idea of getting the vehicles to provide additional sensing information to the infrastructure of SureTrack. All right. So that's going to provide a lot of information. One of the things that's you might ask is like, well, how are you going to get enough penetration to even test it? You know, penetration of people with OBUs on their cars. We're going to try to incentivize people to use these radios and who use those corridors. And so one of our places that we're targeting is the new garage that's being made by the UPMC out there. They're interested in it because one of the reasons making that garage, they had a lot of problems with the communities because that's going to increase traffic. So they're eager to help mitigate some of that traffic, and so they're going to try to, if we can provide a little incentive to the employees there who come out in particular phases and go out in particular shifts in mass, then we can get a reasonable number of CV vehicles out there in densities that we can then do some evaluation. Yeah.
Why can't you use cell phones and GPS or apps?
Well, so I mean, these are like I alluded to that question earlier. So I think in this particular case, I mean, there are a couple answers, none of which are going to satisfy you, but I'll try to give you it. One is that in this particular case, you have fairly low latency. It's not like vehicle to vehicle where you're right next to each other, but you want to have fairly low latency information being sent to the infrastructure if things are rapidly happening. Okay, not always doesn't always need to be low latency, but in this case, okay, I was thinking sometimes it does. Another case is that cell phones are, you could do that. It usually would have to make a loop around, through some backhaul back in. So that, again, it could increase latencies. You're using cell carriers. People will have to have cell phones. If we haven't mandated that everybody has to have a cell phone, but if we start putting their vehicles and then over time the penetration gets much, much higher, then we can do that. But you're right, for testing, we might have been able to use cell phones and equip the cell phones and have those run those apps. So it's possible. I mean, that's all I can say.
It seems that you are mainly interested in looking at flow coming from a larger distance, but a small distance you can somewhat track.
Yeah, I'm not sure. I mean, we're not looking. I don't know. It would be much. I don't think it's going to be much more helpful than.
The data are basically useless. The latency is just, and the GPS on a cell phone is just not good enough.
Yeah, there's a lot of noise. Go ahead.
It seems to me, though, that if you're talking about pedestrians, they're not moving super fast.
Right. No.
So, and as a pedestrian, you don't get any information because you're not going to be carrying around a separate radio.
Right. So I agree with that. This particular application is just focusing on vehicle flow. Some of the other applications I hope to get to, I'll try to talk about how you add pedestrians to that consideration of SureTrack. Okay. So the detection of pedestrians and what their actions are going to be.
I have another question.
Sure.
So when you say improving SureTrack performance, so do you have some estimate how much room for improvement is there?
Actually, not really. So the answer is that we did our initial estimate when we had our initial deployment out in East Liberty. And we had a big improvement over the baseline that was there, which was 40% improvement in like wait times and I guess transit times and things like that. But I don't know how much can be squeezed out of it. We don't have an optimal solution for anything. In particular, it would have to be an optimal solution for a very prescribed problem, and that problem is one of, here's an approximate term, bajillion, okay, different contexts that could be out there. So I think it's very hard to isolate where we could get some approximation on that, you're right. We have not done a lot of work in that, and that's, I think, a useful thing. One of the things we've thought about doing is we do some of the evaluation in simulation also. And so in simulation, one of the things we could think about doing is some possible, it still have to be small scale because of this, it explodes in space, some kind of possible more efficient centralized approach. But I think it's very hard to do it even with many more than like a few intersections.
Also, it's a highly stochastic system. So when you say, is there a room for improvement? So it really depends on the network conditions that exist at that time. But if you know in advance the information, then probably you will be able to make better decisions. Actually.
Yeah, but sort of, I'm wondering if if you're at 90% of
yeah.
Then are you just sort of playing around at the margins?
No, I totally understand. I have.
Is so bad.
But right. So this is
Yeah.
the question: how much, if you had improved sensor, how much?
That's right.
Would you gain?
So what we do know is that we do have poor. I mean, we have taken physical ground truth versus looking at the sensors, and we've gotten lots of error. Yeah, we got lots of error there. So we know that we have information flow that's corrupted. We have noise. So we don't know if that's leading to things, but given there's a certain amount of cause and effect, and certainly having poor sensor information is bringing down our results. So we do believe that. Is that quantified? Is that understood completely? No, it's not. But more than intuition, I think, because we know that there is error in our sensors.
That'd be interesting to backcast if you know the difference between the ground truth and what your sensors are giving you, then see if you run your optimization on the ground truth.
Right.
And see, okay, how many cars per second could we get through this intersection, and then compare that to.
I think we would almost do it the other way around, which is that when we do simulations, right?
The problem is you can't separate this. When you do it in simulation, the vehicles don't behave like people.
No, I know. I was going to say, but here's a thought. I mean, see, that's what we do. But one of the things we could do possibly is introduce noise in our sensors in the simulation, and then increase that noise and watch the results drop. Let's see if the results drop or not. Okay, so that would be one example.
I have some of those results for East Liberty. But
Okay.
So
So that's I guess would be my point is that use the real intersections you have and get perfect information on the real intersections.
Yeah,
with humans, right? And then
It's actually hard to get the ground truth at the resolution that it's making decisions at. Humans, I'm like, yeah, that looks about, and looks about is not going to do it. Okay, so it's hard to get ground truth out there. In simulation, I think is a better place at least to make that initial cost. I agree with you, what you're saying. It's just really hard to get that kind of information that is being fed into the scheduler in the rapidity in which it's being rescheduled.
and if you can model the noise or the uncertainty, then you at least have an approximation of the function between the improvements in sensor variation.
That's right.
To improvements in performance.
That's right. I see the time's going to be short here already. All right. So I'm going to go through a few, and I apologize to any researchers in which I'm going to have to skip. All right. So I apologize for this. I'm not trying to dissuade discussion at all, because that's probably more useful than anything else. So another quick one using SureTrack is this notion of using management of buses and traffic, because they present particular challenges to managing these intersections. And the reason we use the word manage as opposed to something that where you often will see is like bus priority is because we're not really giving priority to buses or priority to trucks. What we're trying to do is manage them better. All right, manage them better. So if a bus, for example, comes up and has a stop right before an intersection, and you know the bus and you know it's going to stop there, and it has no pull off, so it's blocking traffic, why give it a green at that point? Because there's no function and there's nothing that's going to help there. Okay, so understanding about some of the nature of some of the vehicles that are in your network allows you to leverage some of that special information. The same thing with trucks. You might say, oh, this is a great thing, but if the truck's really, really long, the time it takes to get through the intersection, it may be better to cut it off before it goes then and then let it through rather than have the intersection, having this decision point about whether it should be going through or not. All right, so there's information that you can do to manage this better if you know something about them, and particularly these large vehicle structures like buses and things. And so again, with the DSRC radios on board units for these vehicles, they can send information about them. The buses can send information. One of the things that you're going to be doing is you're going to be doing trade-offs, right? Trade-offs between flows, trade-offs about buses. There are different metrics that you might try. One of the common ones, Greg and I kind of disagree about whether we think this is the same kind of metric that we'd want to use, but you might use something like the number of people served by that light. So like a bus, if it's very full, you might say, oh, that has a higher priority than these 3 cars, all right? But at some point, I think the spatial dimensions of 12 cars, which still is less than the bus, but it's a very long line and longer than the bus, may have a preference over that. So that's where we have some little disagreement about it. So at any rate about it is that you need to know sort of occupancy. And so one of the things that we're talking about leveraging is everybody knows the tiramisu application for buses and things. So the tiramisu has talked about providing that information about occupancy for the buses to us, to SureTrack, in addition to you say, oh, this is bus, whatever, and then here's the occupancy of that information, and then you can start doing those trade-offs based on those numbers that you know. I'm going to move on. All right. Aaron and Bernadine have been working on 2 different apps. I talked about Tiramisu, also NavPal, which is to help basically, I think mostly blind, but handicapped people with disabilities to navigate the world and the intersections better. And so they're talking about integrating that with SureTrack via either cellular information. It's not clear, so here's a case where you might do cellular or something else rather than using DSRC to get information about the geometry of the intersections, whether there are any obstructions, try to get more up-to-date information about things that might be stored locally because they can't always go back to this kind of global database. It may take a while for them to come back, where locally you may be able to store that information. And then be able also to give better detection of these people, whether they're at the intersections, whether they're going to try to cross the road. Try to give SureTrack some information so that SureTrack can then try to leverage some of the pedestrian information that comes from them saying, oh, we want to go here and we're walking here and we don't know how to get through here. And so we're trying to give more information to SureTrack to facilitate that while balancing everything else. So that's one of the challenges of OpenStreets, is trying to balance everything out with an efficient flow. Again, the mode of communication it's unclear what's better here. If you want low latency, DSRC is great, but as you pointed out, you're not going to be carrying around one of these boxes unless we can make them small enough and light enough to do that. And the power considerations is one of the big problems for weight. Okay. Real-time routing, wow, it's fast. Real-time routing, again, another thing by Steve Smith, and I'm working with a grad student there where Alan Hawks, who's working on this particular project right now, is for basically, given that you have information of queuing at each of these intersections, you have a notion of the traffic, and you have a notion of backups at each of the intersections. And if you were willing to share the information saying, I'm going to go to there, then it can make routing decisions based on real-time traffic decisions. Oh, it's better to turn left here. Turn left here. And as a result, that has 2 effects. One, it betters your performance greedily, I'm going better. And the second thing it does is it spreads the traffic out, right? So it makes it more equally so it doesn't compound traffic problems. So this is another kind of type of information that can be passed on and that we can try to leverage. Yeah?
I have a question there.
Yeah.
So it sounds like in order to do real-time routing, the user really becomes your enemy, kind of, because to some extent, right? So if you route somewhere where the users are familiar, they have their preferred routes where they like to go, and while it might be more optimal for them to take a different route that might not even take longer, they may just be so entrenched in what they're used to, so that they deviate from that.
So here's where we stand. I say that's current behavior. I mean, that's current behavior, right? And what you're trying to do, this is a social movement change kind of thing, no question about it, where you're saying, oh, look, this guy's saying I'm benefiting, so I'm taking the road least traveled, right? And I'm trying to move on that road. And then over time, if somebody says, how long did it take? Oh, it took me 20 minutes. God, it took me 40 minutes to get there. And so you're hoping that it will convert. If it doesn't, those guys that do adopt the technology early or continue to adopt the technology benefit.
I mean, you also have the issues of, like, oh, this brings me through a neighborhood I don't want to go through.
That's right, that's right. And so I think a more sophisticated algorithm, you start to give preferences on those kinds of things. You're exactly right. But I mean, it's not a perfect thing, but this is a start to this thing. And it's being enabled by this kind of communication infrastructure communication. We are really going to have to fly. So again, this is an attempt to build a more portable ones, at least for bikes and pedestrians. I have never seen this. I haven't seen even the schematics of this, so I don't know what the weights and things are, so I can't comment about how portable is portable. Okay.
And there are, just to mention on that, the small units that they can. It's basically a carrier that you put a cell phone into on a bike, and it converts it to dedicated short-range communication. But it is possible to use some existing chips in some existing phones to be converted to DSRC with existing hardware in phones, and some of the companies out there are pursuing that now. So
right.
That's where it becomes really interesting, when all of a sudden you can just do a software app download to your phone to all of a sudden be transmitting or receiving DSRC.
Yeah.
And that's, but again, that's very possible. And,
right.
But they have to consider the market value of that.
Right, right. So, I mean, certainly it's a big concern, and they're trying to integrate not just vehicles into this network. Okay. This is just something that was, it's a very quick thing. Part of the safety pilot that they had previously in Michigan that Stan brought up, they introduced this kind of architecture for a publish and subscribe architecture where people could publish sources of information, and then applications could subscribe to those data sources and then leverage them to make some decisions. And one of the things is just saying, like SureTrack, we have a great sense of the queues and everything at those intersections at real time, so why not be able to publish that information and have an application be able to leverage it? One of the applications that's already existing there is something made by Lidos, which was a visualization. You can go to a browser and take a look, and you can look at intersections and say, wow, there's a lot of big length of queues in there. Nothing sophisticated here, but just giving a way of tapping into that architecture. Work zone and queue formation notification. The idea here is that on the turnpikes or any kind of arteries where you have work zones that are being set up, or you have backups due to incidences, you have people moving at high speeds and they need to be notified early on. Currently, right now, the notification, if they're lucky, they have some kind of signage early on, but on some incidents, you basically have a police car that's kind of trailing the back of that queue as it gets longer and longer. And so what we're trying to do is provide more of a safety zone in between, and so we will instrument the signs and instrument the cruisers with these radios so that they can send out the messages, so that hopefully people who then have these radios and have the ability to see the messages to read them will be able to be notified of those things and be having earlier things and reduce accidents that way. Okay, so I'm going to just say really quickly something about this whole class of problems. I'm not going to try to be. I apologize to every researcher here just because we're at one. I just want to go to the last couple slides. There is a whole class of problems in which you can instrument the vehicles, or instrument humans, or instrument get information about pedestrians from the cameras, develop models on that, develop models about vehicles, about their driving, develop models about the weather and whether, the detection of whether there are inclement weather, or whether there are vehicles, whether there are road conditions like potholes. And you're trying to take all this information and be able to push it through to the right people. In part, this information will help you to predict the impact of these things. In part, these models will help you to detect when they occur. And so there's two stages to this. The two stages of this is, one, how do you generate these models and how do you form these models, which are very hard. And one of the underlying bases for that is you have to get lots of data. So what we do is we're going to try to instrument a lot of these vehicles, or the humans, or take the cameras, and use the backbone of the infrastructure to send the information to the lights, to send it back to servers over the backhaul. All right, so that's a way of just getting lots of information. They're all in all these applications. There are a number of different types of sensors that are using inertial sensors on the vehicles, camera-mounted ones on the vehicles. All this kind of information just to push it back to the servers so they can do this analysis in order to form these models and make some determination about, where possible, mitigating actions for like either safety or congestion or efficiency. So there's a whole class of these kinds of applications that are being used. And there's researchers, Christoph is doing one on detecting road conditions and weather inclement conditions, sending it back to policymakers, to maintenance people, and also possibly to drivers using maybe DSRC, driver to driver, so that people are aware of those potholes as they're approaching them. All right. There are visual systems for that which are taking in feeds, or trying to detect motions of pedestrians and seeing which way they're moving, trajectories, and using that information such that you can then use the cameras or the radar, I suppose, at the intersections to employ those models to detect where pedestrians are going if you don't have the buttons, or if they were just sitting there, and whether they're waiting or not. And then you can increase the efficiency by saying, oh, I don't have to make this short because there's no pedestrians there, or I better allow pedestrians to flow there. So the first thing to optimizing the pedestrian flows with the vehicle flows is knowing where they are and where they're going. All right. So these are all ways of trying to get that. All right. So there are other applications. I apologize to each of those things, but we're just running out of time. Let me just go quickly to the very end here. Oops, that didn't help. All right. So two things real quickly here. We have there's a program that's for this connected vehicle pilot program, and it's basically being structured for more of an emphasis on I to V and V to I. And the idea here is they had this previous one that was on safety, and it was more V to V. And the idea here is that you have this big Federal Highway initiative. It's going to actually be rolling phases, rolling numbers. So they'll have phase 1 here, and they'll have another phase 1, and then they'll move the first phase 1 to phase 2. And there, as I said, there are 3 phases. The first phase is just planning. You don't do anything other than make sure that you have all your ducks in a row, and you get all your money accounted for, and you have all your community partners, and you have all your con ops and all those things ready. And the second part is to actually deploy these applications that you have out on the field and do the testing in every piece. And the last piece is going to be to evaluate and transition that technology. All right. Between phase 1 and phase 2, it's going to require a separate proposal, so you're not guaranteed that just because you got phase 1, you're going to get phase 2. As I said, it's roll out in waves. We've submitted a proposal, and this thing is currently under review. If it's not this year, we will try again in subsequent waves. And if it's funding, I just want to throw this out there, that if people have additional research topics they'd like to work on the test bed they think fits into that proposal, then in that year 1 early on would be a good time to tell us about it, because we might be able to investigate that for the phase 2 proposal. All right? All right, here's the very last piece. Very last piece, promise you. Okay, all I wanted to say is some of the benefits of the test bed is that it provides a foundation for current and future research. I cannot say this strongly enough, is that without this, you simply don't have enough information. I mean, you don't have enough. You need this to have this nexus for people to do this kind of research. And with this research, as I said, the great thing about it is it prevents us real-time information in a real-time environment. This is, I think, pretty powerful environment for us to do this kind of research, and it'll stand out in the national and world research. So, and the greatest thing is that we're actually doing deployment and transitioning to the real world. So this is a path that goes very quickly. It's not something where we're just working on our IV towers. We're actually going to be able to move to those things. Thanks, everyone. Sorry for the delay. Thanks.